Okay, I think we're looking at Calculus 11 if I'm not mistaken. And what I like to do is usually start with a couple of problems that gave me a little pause in the previous videos. I like to be able to do these in my head quickly and just see what's going on, but out of practice, so just wrote a quick one up here, a couple of quick ones, and let's see if I can just write the answers here, and then we'll do the U substitution. You pause the video, you try it, and gain some experience each time you do a problem. So x to the 6th becomes 6x to the 5th. If I see 3, then it must be 1/2 of, that's the chain rule. Okay. So cosine came from the sine function, and it looks like it's going to be x to the 6th plus c. So if you call that big F, then this is little f on the inside here. And I think if you take the chain rule, 1/2 cosine x to the 6th times 6x to the 5th cut in half is 3x to the 5th. You can check your answers pretty quickly and easily. I said I'd do it with U substitution, so I will. We'll let U equal x to the 6th. So that allows you to write U here. We've got du equals 6x to the 5th dx, which looks very much like y2 minus y1 equals m times x2 minus x1. I thought I'd throw that your way. Next step, du under 6x to the 5th equals dx. That's our next substitution. So instead of dx, we're going to do du over 6x to the 5th. And then we can see the 1/2 cosine u du, which gives us 1/2 sine u plus c. And then you substitute u with x to the 6th. Okay, so now I got a little space. Okay, remember when we do 5x squared dx and then divide by dx, the dx is canceled. So let me get an answer here first. I think that our y prime is going to equal 10x, so minus 10x on this side, minus 4y cubed will become positive 4y cubed. Got to think about the problem, not what I'm saying to you. This one becomes minus 12xy squared. We're going to divide by that, minus 12xy squared, and 4y cubed, positive 4y cubed. So therefore, I think that's going to be my answer. You should, at this stage, be able to write 10x minus 4y cubed minus 12xy squared minus 12xy squared. There's going to be a dy associated with this, so we're going to write y prime, anticipating dividing by dx, dividing dy by dx. It's easier to write that. And then we have 4y cubed with another dy, so we have 4y cubed. And we'll write y prime equals 0. Derivative of a constant is 0. I think we can now see minus 10x, good. Minus 4y cubed becomes positive 4y cubed minus 12xy squared. Okay, so I'm getting a little better than I was 4 days ago. And positive 4y cubed because I can factor out y cubed on these last two terms. And that would be minus 12xy squared plus 4y cubed. So as we go forward from now on, I won't be talking about that so much. We'll just be doing the problem for practice. So we can put it in our long-term memory. And once we start doing that, it's 10 seconds. 10 seconds. Lesson set 18, 10 seconds. Lesson set 19, 10 seconds. Lesson won't take any time. And you'll start to put that in your back pocket. And we'll probably look at some other implicit differentiation situations in different videos. But at least you'll have this one down. All right, so now let's look at point of inflection, concave up. Let's look for concave up. Let's look at the x values for local max and min. Let's write the equation align tangent to the point of inflection. Let's do all of that. Let's do it 2 ways. Let's do it with geometry by completing the cube. And then let's look at it from a context of calculus. All right, so minus b, 6 divided by 6 is 1. So point of inflection occurs at 1. Plug in 1, minus 4, minus 9, plus 10 Minus 9 plus 10 is 1, 1. All right, I'm going to change this number to 11. Now it makes it 1, 2. So we have some different numbers here. All right, so c minus 3ah squared can be done quickly, easily now. So that's going to get our slope at the point of inflection. C minus 5 minus 3 times a, which is 2, times h, which is 2 squared. So that gets us minus 11. Minus 5 minus 6 minus 11. So our equation of the tangent is minus 11 x minus 1 plus 2. And if you wanted to put it in graphing form, you could have written 2x minus 1 cubed, and that's the graphing form for the cubic. So what did we know about this cubic? It had a y-intercept of 11. We knew we were going down at 5 to 1, therefore we knew we had a situation like that because we are decreasing, and y equals x cubed always increases, but once we get those changing, well, that wouldn't give us any local maxes and mins, but as soon as these are opposites, you're going to get local maxes and mins. Now, if this was positive, it doesn't necessarily mean you're going to get local maxes and mins. You might, but it's going to happen quickly around near the point of inflection. Probably. You have to look at the coefficients of these terms. All right, I digress. My apologies. All right, so what is the x value here? And the x value here, it would be, that x value would be measuring from 1 forwards and backwards, just like the quadratic formula. And it's the interplay of the slopes of these two terms. So we're going to look for slope of 11, positive 11, and 3 times 2 is 6. And those are going to be our x values of local max and min. Now, I'm talking to you, but you can do all of that in under a minute once you get the hang of it. So now let's validate that with calculus and answer some of the concavity issues here, because I didn't answer those yet, although I think we already know. So y prime is equal to 6x squared minus 12x minus 5, and at x equals 1, that's where the vertex of that is, the vertex, and the quadratic is measuring rates, and that's going to be our minimum rate right there at x equals 1. And so we got to plug 1 in now to see what the rate is at the point of inflection. So minus 6 minus 5 minus 11, we knew that, minus 11. And if we put 1 in, we've already done it. We got 2 out, I think, didn't we? We got 11 out. What did we get? 2. Right? When I put 1 in here, excuse me, the position. Position function at 1 is 2. Rate function at 1 is minus 11. And what am I missing? Y double prime in order to talk about concavity. So 12x minus 12. All right, that's an increasing linear function. Let's see if I can draw it real quick here. All right, so we're going up at x equals 1. We get a change from negative to positive on that linear function, which means concave down, which we saw, and then positive concave up. So when are we concave up? For x is greater than 1. All right, we got enough practice with that. There might be some other things to say, but we're trying to get in a decent calculus practice. And so if you want to learn the geometric aspects of what that cubic is all about, go to the playlist on cubics and look around. All right, so you're estimating the cube root of 8.1. We've been estimating square roots. All right, now we're doing a cube root. And so how do you do it? Do you recall how we did estimating values, approximating values like that? Well, I hope ELT popped into your head. Equation of line tangent. Cube root looks like this. At 2, you're at 8. I'm sorry, at 8, you're at 2. At 8, you get a 2. And the tangent line is almost identical to this little situation right here. So we got to take the cube root of x, but we'll write it as x to the 1/3. And so our derivative of x to the 1/3 is 1/3 x to the minus 2/3. So you can do this in your head. You can put 8 in, keeping in mind what that is. You've got a change of 1/10 here. So x minus 8. When we put in 8.1, we're just getting 1/10. And we're going to add that to 2, whatever this multiplier is, and we're going to get it right now by dropping in 8. Cube root of 8, 2 to the negative 2 is 1/4 times 1/3 is 1/12. So what's a good approximation? 2 and 1 over 120. And that's probably pretty darn close. Might even get close enough to say within 10,000th of a decimal place. I don't know, guessing. Making some room here. Now we're going to do some very quick derivatives just to get some of those derivatives to be in your long-term memory. So f, each of these is the function f. What's f prime for tan x? You pause the video, I'll just keep going. Derivative of tan is secant squared x. So big F, we'll call that little f. Or I guess down here I had f and f, little f and f prime. Okay, so that is the notation. We should be familiar with it now. So that was tangent x, became secant x. What's the derivative of secant x? Secant x, tangent x. What's the derivative of 1 over x? I hope you're not saying ln of x because that's integration. 1 over x, or x to the minus 1, becomes minus 1 times x to the minus 2, which could have been written as minus 1 over x squared. Okay, so that's the derivative of that. The 4th root of x to the 5th could have been written as x to the 5/4. So we have 5/4 x to the, I hope you're subtracting 4/4. Hope you're getting quicker with that, and that gives us 1/4. Okay? All right, so those were just some quick derivatives. This we've done already. We've done that. We've done that. So we're going to the other side of the board. Bear with me. Let me hibernate. That was a very bad joke. All right, mean value theorem for derivatives for x cubed minus 2x. You're pausing the video and you're saying, do you have any understanding of the mean value theorem for derivatives? You know that value c. That's how it's written in the textbook. C, which is an x value. What x value is it? Where the curve, providing it's continuous and differentiable over the open interval, that's continuous. We can differentiate everywhere, except at the endpoints of the interval, because that's one-sided. We don't know what's on the other side. Okay, so we've got to find the average rate of change from 0 to 2. The average rate of change of x cubed minus 2x. X cubed minus 2x probably looks like this. That's probably what it looks like. We've got a 0 here, so it goes through the origin. It's got roots at 2 and 0 and positive root 2, negative root 2, I guess, and 0 if you factor that. But we're after the average rate of change from 0 to 2. So from 0 to 2 is probably something like that. Well, let's find out. Put in a 0, you get a 0 out. Put in a 2, 8 minus 4 is 4. So 4 divided by 2 is a 2 to 1 ratio of change. Where is it going to be going up at 2 to 1? Probably right about there. I could draw something that's parallel for a tangent. And so we got to have the derivative of x cubed minus 2x, which is 3x squared minus 2. So we got to bring the 2 over, we got to divide by 3, and we got to do the plus minus square root. And so a little bit more than 1 unit to the right. Right there, we're going up at 2 to 1. There had to be at least one place. All right. So how about the mean value theorem for integrals? Just mentioned that yesterday, I think, in Calc 10. And I like to see something done 4 days in a row before I worry about somebody not picking up a concept, or at least some mechanics, or moving forward with a problem. So x cubed, let's just call it, there's x cubed, but let's look at from 0 to 2. So from 0 to 2, we've got something like that, right? 0 gets you 0, and 2 gets you 8. Okay, so here's the x-axis. We're going to look at the area under the curve. and we're going to divide it by b minus a. 2 minus 0, because that's the width. And when you divide area by width, what do you get? Area divided by width is height, and that's a rectangular shape. And I think the height we're looking for is right about there. We want to find that height. And the way we find that height is we reshape, right, as a rectangle. And so that height is our average value. All right, now let's say we had people getting sick per week with COVID, right? And let's make this 100,000 people. All right, for the longest time, the number of people getting sick was the area under that curve, right? But if I wanted to go to, say, over here, well, all of a sudden, we're accumulating area very quickly. So the average value may not be all that important as to what was the average number of people getting sick from 10 weeks ago to 10 weeks from now, whatever. All right, awkward language here. What would be important would be really looking at what's happening right now. All right, and making some public policy decisions based on more recent situation. All right, so I'm blabbering here. So how do I find the area under the curve? Or a little practice here. So the area under x cubed dx from 0 to 2. And that's all we're going to do with these things is just write the calculation. We might calculate once in a while, but just getting familiar with mean value theorem for integrals. All right, we'll formalize it a little more later. All right, so dy dx equals xy. Curious if anybody can just answer the question yet. With a 0 getting 10, getting back into the swing of this. Pause the video, but we're going to solve for y, and y is going to equal 10e to the x squared over 2. That's where we're going to go. How are we going to do it? This is multiplication. Multiplication by y is division by y on the other side, and that probably would be more recognizable if I multiplied by 1 over y. Okay? And over here we're leaving the x and we're bringing the dx, and that's one layer of area under a curve. One layer. Okay, with a height of x and a width of dx, and there's probably a whole lot more that we're going to look at in order to get to this. Right. So if I integrate, and I integrate, I get the ln of the absolute value of y. Moving the c to the other side gets me x squared over 2 plus c1 added to c2, or taken away from c2 gives us c3. We'll just call it c. We'll do e to the gets you plus or minus e to the x squared over 2 plus c. And that's the same thing as e to the x squared over 2 times e to the c. So we're going to call e to the c a. And I got a plus minus here. I don't care about the minus because the 0 gets me 10. E to the 0 is 1. So that's where your 10 comes from. Okay, and the first stage of learning is following. So if you didn't follow, look at it again tomorrow. You'll get a little further along. And if you start following it, then next time we do a lesson set, if you see the rate of change of a function has something to do with itself, well, the rate of change of e to the x is e to the x, so it's going to be a hybrid of that. All right, very early here. Some quick integration. We'll just do it orally. All right, so what does x squared become? X to the 3 over 3. What does x to the minus 5 become? Remember, I got to add 1. So x to the minus 4 divided by minus 4. Okay, so let's put the minus out here. 12x to the minus 3. Well, that's basically the same question, so we won't even do it. 4 over x plus 4 ln of the absolute value of x plus c. We got a little bit of integration practice. Okay, moving right along. On the end, on the other side of the board, we're going to look at derivation from geometric and graphical context. All right, a little different part of the brain. All right, so first quadrant area, y equals x cubed, y equals 125. Let's do it in terms of x, and then let's do it in terms of y. So at 125, We got x cubed. We're going to go from 0 all the way up to 5 gets us 125 because it was the y value that equals 125. So 5 times 5 times 5, 125. So if we're doing it in terms of x, we have the top function, which is x cubed. We have the bottom function, which is y equals 0. So we have x cubed minus 0 and tend to not write that. We tend to not write that. So we're going to integrate x cubed, give all those little altitudes, they're cubing whatever this x value is, and that width dx, replicating 8.01. However many zeros I just said, multiply that number times 10 and one more time after that. And that's how many of these rectangles, which look like thin strips. Hope you can see there's still area there in that thin strip. Alright, so we're going to go from 0 to 5, and we're going to get x to the 4 over 4 from 0 to 5, which is equal to 5 to the 4, 625 over 4. Now we should be able to get the same answer if we do it with horizontal rectangular areas, which means this is an x value, and that x value is a function of y. For instance, what's that x value? It's 5. Well, how do I get that 5? Well, what's the inverse of x cubed equals y? I think it's x equals the cube root of y. What is the cube root of 125? Oh yeah, it's assigning these distances. The cube root of y, which is y to the 1/3. But I'm not measuring left to right. I'm measuring those, I'm stacking them up vertically. So I have to go from 0 to 125. And these things are dy's right there. Now I'm not done yet here. Right? Because there's an x distance here too, and we don't want that x distance, right? It's okay right there, but it's not okay there. So then the question is, what am I subtracting? What is that x distance? Well, it starts from this x distance, which is actually 5. And let's say that this is also 5, right? This is also 5, but I have to take this away. All right, so what am I taking it away from? Well, I got to find this value. I got to take that away from this. All right, I got to take 5 minus this part right here. And that part, that x distance, is coming from this. So this was a little awkward, but it's first time. So it's really 5 minus y to the 1/3. Now let's put a y in there that's friendly. What comes out that's friendly? Cube root. 125. 8. I can't figure out cube root of 8. Anyway, this is the equation, and it should come out to 625 over 4. So 5 dy becomes 5y minus y to the 1/3. Add 1 and divide 4/3, 3/4 y to the 4/3. Fortunately, we still have a 0. We're going up to 125. So let's drop 125 in. Cube root of 125 is 5. 5 to the 4th, 625. So we have 5 times 125, which is 625, minus 3/4 of 625. Let's do it that way. Turns out to be 1/4, right, of 625. Yeah, I guess you saw all of that. They're the same. Right? It's a little awkward when you're doing something in terms of x for so long, your entire math career, f of x, f of x, f of x, and now we're doing x as a function of y. Yeah. Takes a little time to iron that out, but we got the time. All right. Now, let's go from 0 to 3 pi over 2 cosine x dx. Can you draw the picture? From 0 to 3 pi over 2 cosine x dx. Can you draw that picture? Well, I hope you're drawing the cosine function. There's the first period. Here's 3 pi over 2. And we're going to collect area here. Yep. Now it looks like if that's all the area, this is positive area because I'm moving to the right, which is a positive width movement, and I'm looking up, which is a positive width movement. I'm still looking to the right, which is positive, but I'm looking down, which is negative. So we're accumulating negative amounts by this. And it looks like those cancel each other. And I got a feeling this is going to be 1. We'll find out why. Well, not going to find out why. We'll find out how it becomes 1. The why is still bothering me and has bothered me for I can't tell you how many years. I do know that sine squared plus cosine squared equals 1, and I do believe there can be some sort of ratio of change there that will help me see that. But if somebody knows, because I'm not a math major, if somebody has done that out and actually can put in the comments why it's 1 besides mechanically, that would be great to find out, because I don't think I'm going to figure it out. But I'm going to keep trying. All right, so what did the cosine curve come from? Sine curve. And we're going to go from 0 to 3 pi over 2. Okay, so here's 0. We're going to go to 3 pi over 2. We're going to look at that location on the unit circle. And yes, looks like minus 1. I misspoke before. I forgot about the fact that it's negative. I was just saying, because the sine function, that first part of the sine function is 2 units of area. So that was what was in my head. So it should have been negative 1. Corrected. All right. Sine of 0 is 0, right? All right, so now we get to look at something entirely new. Shout out to Monty Python. Something completely different. Yeah, it's not completely different. It rests on the concepts you've already learned. All right, so I'm drawing little g. This is the graph of little g of x, or I call it gt. All right, doesn't matter. That's a dummy variable. Let's just say it's little g. All right, and I want to find out what this function looks like given these numbers. All right, we don't know what happens after x equals 4 or to the left of negative 4. This is all you're looking at. All right, what might be the most helpful here? The most helpful here might be, give me a drawing of the shape of big F based on what you're looking at, and that'll take a little bit of thinking, and I'll get you through the first step. How are G and big F related? Well, I need, to answer what this looks like, I need f of x. And we haven't done it very much. Once or twice and not consistently. Okay? But if we did this out, we'd get big G of t, so repeating something from an earlier lesson set. All right? And we would have to drop in a 2 and an x. And so if we did that, we would get G of x minus G of 2. And if I took that derivative, I get little g of x minus 0. Oh, I guess f of x is equal to g of x. So I guess this is the derivative of big F. Okay, now try to draw the sketch. What might it look like? And maybe you start on the left side and ask yourself, what are these y values telling me? Each y value here is the slope of a tangent to big F. So what's big F doing here? It's going up at 4 to 1. And it does it for 2 units. So let's say we go up at 4 to 1 for 2 units. And then what happens to these slope values? Well, it becomes 3, becomes 2, becomes 1. Right? So it becomes, instead of going up at 4 to 1, 3 to 2 to 1, and then it's 0. And then what? Minus 1, minus 2, minus 3, minus 4. Minus 1, minus 2, so on and so forth. Right? And then when we get to here, we have a constant rate of change of down 4 to 1 at a constant rate. Okay. So I have a constant rate of change. I have a concave down interval. And then I have another constant rate of change. So this is the first derivative. And what's happening to the first derivative from here to here? It's decreasing. And that matches up with concave down. So when is this function concave down? From -2 to 2. Big F, concave down from -2 to 2. Now, can we attach some numbers here? Can we put some numbers? Not that this is drawn to scale. It's not. And maybe we doctor it up a little later. Well, there's one thing I definitely know. I know an x value that will help me out. What happens if it was 2? How much area accumulates? Because that's what this is all about. Area accumulation. I don't think I have any area from 2 to 2 to accumulate. And I think that happens right here. So therefore 2 gets me 0. Okay. Boom. Let's just put a little mark there. Oh, well that looks nice. That's a nice rectangle. I think I can figure out that area. My width is 2. My height's -4. I think it's -8. I think at 4 I'm at -8. Did that capture it? Yeah. And it looks like when I go to the left, I'm moving back, which is negative. But I'm also looking down, which is negative. So I'm actually going up. Yes, I am. Until what? I get to -2, which I now know is here. -2 also gives me a 0. Why? Because negative times negative is positive area. Going up as I look backwards, as I looked into the future, yeah, I'm going down. So if I look into the past and rewind, I'm going up. And then this is negative area. They offset each other. So I'm right back to 0. And then I got another one of these. But I'm looking left now, which is a negative, and I'm looking up, which is a positive. So I'm accumulating -8 units of area. So at -4, I'm at -8. Hope I didn't botch that. So what would the equation of the tangent line be at 3? Well, at -3, excuse me, at -3, I'd be right here at -3, and that would be half of that, so that would be -4. So I would have x plus 3 minus 4, and then I need the slope there. Well, the slope is 4. Remember, it's the y, well, no, yeah, it's constant, so it's there. I put it at the wrong place, but it's still 4. So I'm going up at 4 to 1. And that would be the tangent. All right, so that's what f of x looks like. And I think I've done justice to the cause here. I hope I haven't made any mistakes. And it's the first time doing that in many years. So the language might be a little awkward, but we'll hopefully refine it as we repeat. I'm a big fan of repetition. Yeah. Especially practicing things you're not sure of. You just keep chipping away at it until it comes into focus. So we'll keep chipping away at this. No pressure. Nobody's testing you. I mean, I would test you regularly just so you could see your progress. You know, the scores usually go from about 5 to 10 right answers. And at the end of the semester, the top 2 students are getting somewhere between 100 and 120 right answers. So, and it happens pretty quickly. So that's just a little different approach. All right, so I'm babbling. And I'll upload this when I get the chance.